Okay, a power plant generates 125 megawatts of power. How much energy does it generate in a day? Okay, we can figure that out. That's not hard. Okay, so we're just going to use power is energy over time. So therefore, energy, right, is going to be power times time. So that's going to be 125 times 10 to the 6th, and that's watts. That's joules per second, right? Times, and it's 1 day, right? So it's 24 hours per day, okay, times 3,600 seconds per hour. I'm just putting units on here. Normally I don't do this, but I just want to show you something here. So hours cancels hours, seconds cancels seconds, and you'll end up with joules per day, right, which is what we want. Okay, so 125E6 times 24 times 3,600 gives us a really big number. That's 1.08 times 10 to the 13th joules. Okay, so that's that, right? Okay, so now the question is, if it's only 37% efficient, that's the output, right? This is our output. Okay, efficiency is output over input, so therefore the input, which is what they're asking for, right? The energy input is going to be output divided by the efficiency, right? So it's going to be 1.08 times 10 to the 13th divided by 0.37. So take that, divide by 0.37, and you get roughly, it's 2.9189, so 2.92 times 10 to the 13th joules. And this is our input, right? Okay, so we got that, right? How many kilograms of coal would you burn? So let's figure this out, right? Okay. How many kilograms of coal do we burn? Well, the energy is the mass times the specific energy, right? So therefore, the mass is the energy divided by the specific energy, right? So that's going to be our 2.9, I'm going to go 9189 E13 divided by, and then for coal, they're telling us to use 40 megajoules per kilogram, right? So that's, and this is joules, divided by 40 E6, and that's joules per kilogram. And this will give us kilograms of coal. Okay, so that guy divided by 40 E6. Wow, that's a big number. It's really not helping me out here. So it's 1, 2, 3, 4, 5. So 7.30 times 10 to the 5th. Okay. It's 729729, right? So we would, oh wow, that repeats. That's a cool number. But anyway, so then we'd say 7.30 times 10 to the 5th. And that's a lot, right? That's 730 metric tons. A metric ton is just 1,000 kilograms. Okay. And of course, the energy density of uranium is a whole lot more, right? Notice this is 8 times 10 to the 7th megajoules, right? So that makes the energy density of it 8E13, right? 8 times 10 to the 13th. And what I'm doing there is megas to the already to the 6th. This is 6th times 10 to the 7th. So you just add the exponents there, right? So it's going to be 10 to the 13th. So the energy, if you just use uranium, then that's going to be the same energy, right? So the 2.9189 E13. But now we're dividing by this fantastic, number, which, and by the way, when you look at the energy content of uranium, you'll get, depending on what they factor in, you'll get different values, but let's just go with what IB thinks it is. And you can see here now it's going to be less than a kilogram. So take that energy, divide by 8E13. A round number like that is highly suspicious, right? And that's 0.36, it's 4/8, so I'll say 5 kilograms, right? Which to me, I mean, 125 megawatts, a coal plant, is good 500 megawatts or so of power. So that's kind of like seems like a lot of uranium, especially when the waste products from this are going to be around for 10,000 years. But anyway, but compared to coal, I mean, the benefit of nuclear power, right, is it doesn't have any direct scaled greenhouse emissions. There are greenhouse emissions in mining it and all that, but it's less certainly than coal.